This lesson is going to be about angles and radians. This is the start of Chapter 4, or Chapter 4.1. So today we're going to talk about degrees versus radians. What's the difference between them, and how do we convert between the two of them? After that, we're going to go through some standard terminology for angles, so we're all going to be talking on the same page. And then finally, we're going to summarize with a couple of things. I want to describe them almost as physics, but this is going to be talking about speed and motion and the length of a circular arc. Okay, these will lead into some of the discussion later in this chapter. Okay, first off, what is an angle? Okay, an angle is basically formed when I have two rays that have a common endpoint. One ray is going to be called the initial side, and the other ray is the terminal side. There really isn't anything we just choose to usually call the smaller of the two angles, because if I switch the two sides, then I can end up with the larger angle. But normally we stick to the smaller angle, okay? But not always. So if we have one initial side and one terminal side, then the angle is going to be measured from the initial to the terminal. We always tend to go counterclockwise, or basically how my right hand would tend to move. Okay, if I'm trying to close my hand in a fist, then that's the direction that we're going to be measuring our angle. Okay, a couple other terminology. Point B is going to be called the vertex. We frequently use the letter theta to represent the angle, but it's not the only letter that we use. We have several other Greek letters that will sometimes show up. The second letter there is phi. It kind of looks like the empty set, but it's a Greek letter phi. Alpha, beta, could be almost any letter. Sometimes if we feel like not going into the Greek letter system, maybe we'll use T, or even like angle A, B, C, okay, where B is the vertex. Some important points to remember out of this. Okay, the angle is going to be measured counterclockwise. Okay, again, from using your right hand, it's the direction that your right hand closes. Clockwise would be a negative angle. So if I measured the other direction, I would end up with a negative angle. That angle basically being negative 360 minus theta. Okay, and the other thing to remember, okay, is that basically that whole 360, that's because the angle is basically going to be just a portion of a circle, a fraction of a circle. Okay, so there's our circle. Okay, so the standard position to provide a common starting point, or basically an origin for our angle, okay, the two rays can be placed on an XY rectangular coordinate system, okay, kind of like this, okay, but because we want the initial side to always be aligned with the positive x-axis, so we can basically just rotate the angle, okay, so that the initial side lines up with the positive x-axis, and see the ray BC is wherever it's going. Okay, the angle doesn't change just because I rotate the picture. Okay, and in this case I'm going to use the letter alpha just so we get used to using different letters. Okay, but angle alpha is positive, again, because it's measured counterclockwise. Okay, angle beta, if I was to measure that, okay, that would be the negative version. Okay, however, they are identical. Okay, they're the exact same angle. It's just a matter of which way you measure it, in the positive direction or in the negative direction. Okay, normally we want to stick with the positive. Okay. Couple more terminology, okay? A quadrantal angle, okay? A quadrantal angle is basically when the terminal side, okay, the ray BC, lies along one of the axes, okay? In the picture shown here, it's lying along the positive y-axis, the red arrow being the terminal side, okay? This is also a quadrantal angle where my red ray is along the minus x-axis, or in this case, the minus y-axis. Okay, so those are quadrantal angles, 90, 180, and 270. Okay, an acute angle, however, is any angle where that's going to be less than 90 degrees. So all of these angles, as the red arrow basically moves, anything from 0 to less than 90, so it would be parentheses 90, okay, is an acute angle. A right angle is a quadrantal angle, but it's going to be an important one because the angle is then going to be exactly 90 degrees. Okay. A lot of times we'll, instead of using a curved angle, we'll use kind of a square angle indicator. And I don't want to do it here, but we've seen it before in other classes. Okay. An obtuse angle now is going to be any angle that's going to be greater than 90 degrees. Okay. Again, because we're talking positive angles, it's going to be the positive angle here is going to be greater than 90. So basically from 90 to 180, again, not inclusive. So 90 would be a right angle, so an obtuse cannot be a right angle. And a straight angle, which is the next one, a straight angle, which is the next one, is exactly 180 degrees. Okay, so basically it's a straight line, but we still call it an angle. Okay. And by placing the vertex at the center of the circle, we're basically talking a central angle. Okay, so degrees and radians. Okay, historically, a circle will have exactly 360 degrees. I believe this is from one of the ancient civilizations, Babylon, I believe it was. They came up with this measurement. They had a base 60 mathematical system where instead of counting from 1 to 10, they counted from 1 to 60, actually 1 to 59. And so they broke a circle up into 360 degrees. And every angle, okay, will therefore be between 0 and 360. Okay. Angles greater than 360 can be reduced by basically subtracting integer multiples of 360 degrees. So for example, if I had an angle of 1170 degrees or 1170, that's basically 90 plus 3 times 360. So I can reduce it by subtracting all those 360s and to get a 90 degree angle. In terms of radians, okay, a circle will have exactly 2 pi radians, okay, where the definition of a radian or 1 radian is the angle whose arc length, okay, basically how long the going around the circle is, when that equals my radius. Okay, so it would be an equilateral triangle if it was a triangle instead of an segment of a circle. Okay, so remembering those two facts, okay, that a circle is both 360 degrees and 2 pi radians, okay, that allows us to convert from degrees to radians and radians to degrees. Okay, so if I'm going from degrees to radians, I basically multiply the degrees by 2 pi radians over 360 degrees. Okay, this is similar to what we did in science classes when we did dimensional analysis. Okay, so in this case, I basically have 45 degrees, okay, times 2 pi radians over 360, and my degrees now are going to cancel, and I'm basically left with just radians, and then going through the math, I basically end up with 90 over 360 on top, or pi over 4 radians. Going the other way, it's the same concept, okay? It's dimensional analysis, except now I'm going to be multiplying by 360 degrees divided by 2 pi radians because I want to end with degrees. So if I started with pi over 3 radians, I'm going to multiply by 360 over 2 pi. Again, my radians is going to cancel, and I'm basically left with just degrees. In this case, 360 divided by 2 pi times pi over 3. My pi's also cancel, and I'm left with 360 divided by 6, or 60 degrees. Okay? So, a couple of common angles. Okay, we will be using these angles fairly frequently throughout this unit and throughout all of this year. It's worthwhile remembering these angles in both radians and degrees. Okay, and the easiest way to do this is just to remember the base numbers, 30, 45, 60, 90. Okay, and the radians corresponding to this would be pi over 6, pi over 4, pi over 3, pi over 2. Okay, everything after that is just basically going to be multiples or additions of that. Okay, so in degrees it becomes 90 plus 30, 45, 60, 90. And then 180 plus 30, 45, 60, 90. And then 270 plus 30, 45, 60, 90. Okay, in terms of radians, it's more or less the same thing. Okay, and I'm going to take pi over 2 plus pi over 6, which becomes 2 pi over 3, then 3 pi over 4, 5 pi over 6, etc., etc., etc. Okay. I would recommend that you pick one of these that you're more comfortable memorizing, either the ones in degrees or in radians. Okay, and memorize those angles going forward. Okay, best would be to memorize both. Okay, and so that's what I mean by these common angles are repeated in all four quadrants. It's basically 30, 45, 60, 90 in both directions. Okay. You could also do the same thing going in the negative direction, in which case you have minus 30, minus 45, minus 60. It's useful to be able to think in both directions, because sometimes it's a little bit easier to think in terms of the negative direction. Okay, so coterminal angles. Okay. When two angles have the same initial and terminal sides but different rotations, they are called coterminal angles. This is what happens again when you go more than 360 degrees or more than 2 pi radians. And so to get to the coterminal angle, we can either add or subtract multiples of 360, integer multiples of 360, or 2 pi radians. So, for example, in the case of 400 degrees, okay, 400 degrees is equal to 40 plus 1 times 360, or if I basically subtract 360 from 400, I find that 40 is the smallest positive coterminal angle. Okay, I could find another coterminal angle by subtracting another 360 from it, in which case I would end up with minus 320. Minus 320 would be the smallest negative coterminal angle. By subtracting or adding multiple integer multiples of 360, there are effectively an infinite number of coterminal angles. Most of the time we're only going to focus on the smallest positive, or in some rare instances also the smallest negative. Okay. Working in radians now, okay, if I had 13 pi over 5, okay, well, 13 pi over 5, if I was thinking in terms of 2 pi is 10 over 5, and so 13 is greater than 10, so I know I've gone past that 2 pi radians. So I can subtract out that 2 pi, or the 10 over 5, and I end up with 3/5 pi being the smallest coterminal angle, positive one. Looking at the negative number, okay, if I had a minus pi over 15, okay, well, minus pi over 15, to get to a positive, I basically have to add 2 pi radians in this case. Okay, if it was in degrees, I'd have to add 360 degrees. But in this case, it's minus pi over 15 plus 2 pi. Okay, 2 pi being 30 over 15 pi. Okay, I need a common denominator. So after I simplify it, it becomes 29 over 15 pi. Okay, arc length. Okay, the arc length S is basically going to be just a portion of my circumference. Okay, circumference being 2 pi r. So I can basically make a proportion that says theta to 2 pi, okay, the full circle. What fraction of the full circle am I? Okay, well, that's going to be the fraction. S is then going to be the fraction of my circumference. Okay, or theta divided by 2 pi is equal to S divided by 2 pi r. Okay, after multiplying by both sides by 2 pi to basically get rid of that, Okay, so if I multiply both sides by 2 pi, I end up with this that says theta is equal to S over R, or just to organize it, sometimes I'll also have that the arc length S is going to equal the angle theta in radians. Okay, theta must be in radians. Okay, so theta in radians, if you're going to do it in degrees, you'd have to work on it and say it would be what portion of the circle is theta divided by 360. Angle in degrees, okay, what fraction of the circle basically is it? Okay, so linear angular speed, okay, this is where we start to look at it a little bit from a physics standpoint. Okay, so if a point is in motion on a circle of radius r, through an angle of theta radians in time t, then its linear speed, or how fast it's going, okay, is going to be given by the distance arc length s divided by that time t. In this case, the theta in radians could very easily be greater than that 2 pi. If it goes fast enough, it'll go more than 2 pi radians in 1 second. Okay, so that's why we had to do the coterminal angles. Okay, so S is the arc length now, given by S is equal to R theta, okay, theta in radians, and its angular speed then is how many radians is it making per second. Okay, we could do it in degrees, but we're pretty much going to stick with radians here. Okay, so omega, that little Greek letter kind of italicized W, okay, it's actually the Greek letter omega that we're going to use. That omega is going to be the radians per second, or theta divided by t. And so to convert between the linear and the angular speed, okay, the linear speed v is going to be the radius r times the angular speed. Okay, so just remember that. Okay, they're both going to be going from linear to angular. Okay, so this is the linear distance s, and the angular is theta. We multiply that by r, and in this case linear is velocity v, and multiply my angular omega by r. So the Greek letter is always going to be the angular one. Okay, the linear one is going to be in regular English, regular letters, and either way we multiply the Greek letter angular one by r to get the linear one. Okay, thank you. Oh, so here's an example. Okay, I want you to try doing this one at home. Basically, before iPods, we had records that used to spin. CDs still spin. They actually spin pretty fast. But a 45 RPM, RPM stands for revolutions per minute, basically full circles per minute. So in 1 minute, it would make 45 rotations. Okay, so the question is, find the linear speed in inches per minute. Oh, actually, don't do it in inches per minute. Yeah, well, let's do it in centimeters per minute. Okay, find the linear speed in centimeters per minute at the point where the needle is 7.5 centimeters from the record's center. Okay, so my radius is going to be 7.5. See if you can find the linear speed for that, and we'll talk about this in class. Okay, thank you.